So when we say exponentials, so we'll start with exponentials. When we say exponentials, we mean normal things. If it's as high school, use the word indices. That's just that. Like y is equal to 2 to the power 3, to 2 to the power x. This is an exponential function. Like 2 to the power 4. Where we say this 2 is named as the base. This 4, which is a power, is also called an exponent. And that's where the term exponential comes in, just dealing with powers. And so you can do so much here. For example, we understand that if you're dealing with maybe 2 to the power 3 and to the power 2 multiplied by 3 to the power 2, because the powers are equal, we can as well write this as 2 by 3 to the power 2. The values will be the same. Let's check if that is true. This is 4 multiplied by 9, giving us 36. This is 6 squared, giving us 36. So either ways, we're getting the same value. So if we have something like, okay, the same 2, then to the power 2 plus 3. Maybe let's start with the complicated one. 2 power 2, and then we multiply by 2 to the power 3. Oh, if we go down, this is 4 multiplied by 8, giving us 32. Well, instead of multiplying, squaring this side and then getting 2 to the power 3, we can as well choose to just get a 2 and add these 2. So we add 2 plus 3 because the base is the same. So what we'll get is 2 to the power 5, which is equal to 32. And you can see that these are equal. If we have 2 to the power, let's say 4 here, and then divide by the same 2, maybe to the power 7. Well, this is like 2 multiplied by 2 multiplied by 2 multiplied by 2. That's what the power means. This is 2 multiplied by 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 2. So we have 1, 2, 3, 4, 5, 6, 7. So we know that we can cancel this. We can cancel here. We can cancel here. We can cancel here. So we're remaining with 1, 1, 1, 1. 1, 1, 1, 1. So 1 times 1 times 1 times 1 times 1, we just get 1. And 1 times 1 times 1 times 1 times 2 times 2 times 2. This is 4. And then by 2, so we'll have 8. Oh, one can say, oh, maybe this would take time. Why can't I just write this as 4 and then subtract 7? Since the bases are the same. So this is going to be 2 to the power negative 3. Realizing that there's a negative power, then you write this whole thing under 1 as a fraction. And then once you take it in the denominator, the 3 becomes positive. And then we have 1/8. You can see that they are equal. So we can do so much here. What happens if we have, let's say, a 5/7? This is to the power 2 and also to the power 2. Now maybe we start it the other way around. If this is 5/7 to the power 2, well, 5/7, if you have to divide here, we'll get decimals. It will be decimal number. So you say, maybe it will be tricky to get the square of a decimal. Why can't I just give 5 this 2 and do the same to 7 and leave my answer as a fraction, 25/49, like that. So we can do so much here. So if we can use this guy, then we know that, let's see, if I have 2 to the power 1 over 2 to the power 1, using this property here, we can write this as 2 to the power 1 minus 1. That is going to be 2 to the power 0. Then it means 2 to the power 0 is 1. Why? Because we know 2/2 is 1. So all these put together, they are going to give us some nice properties of indices, of exponentials. So now we write properties of exponentials. Hello.
On your previous explanation on those tools, I didn't get anything.
Of which one?
That 2/1 divided by 2/1. What are you trying to explain there?
They are just trying to see what the value of 2 to the power 0 is going to be.
Okay.
Yes. Okay, so we have one. We now want to write those in a formal way. So we'll start with the first one, which we said any number to the power 0 is actually 1. The second one, we said if we get a to the power m multiplied by a to the power n, if the bases are the same, then we can just add the powers. The third one, if we get a power m and divide it by a power n, and then it's the same thing as getting a m minus n. So when two things are equal, it does not mean that you have always to start from the left-hand side. You can start from either side. You can use n of them if you are given the other. What else? If we are given a, you are multiplying it by b, and the power is n, you can choose to write this as a to the power n multiplied by b to the power n. Like that. Maybe we just make it simple for us that if there will be a to the power negative n, we shall be quick to remember that this is just 1 over a to the positive power n. Well, should there be a fraction? Maybe it can confuse us. A to the power m over n. Well, this can also be written as n. So it will be the nth root of this a, everything to the power m. Everything to the power m. These are the rules of exponentials. And we have seen this, we've seen where they're coming from. We could demonstrate using these numbers here. So what goes around? If this is 2 here, if this is 2 here, same base, we can add the powers. The bases are different, but the power is the same. We can do a split. If this is 4 minus that guy, well, it can also be written as a fraction. So you also see that if the bases are different and then the power is the same, we can also split like that. And I've seen that 2 to the power 0 is 1, and this is where it's coming from. So that's how we get all these things here. So these are the properties that we need. Oh, but we also have logarithms. We also have logarithms. Or maybe let me put this on the other page and then I'll come back and do the properties on the other page here. So let's talk of logarithms. Now that we understand exponentials, and we have seen that for example, if we want to deal with y is equal to a to the power n, well, let's put power x, a to the power x. We have called a the base and x the exponent. Here's what happens when you hear that there's logarithms. If they ask us to say, given y is equal to a to the power x, find x. Look at where x is. X is in the power. How then do we bring the power down? How do we find the value x? Well, if we have simple things like 9 is equal to 3 to the power x, then we know that we can write 9 as 3 squared. Since the right-hand side is 3x, then we'll say 2 is equal to x. That one we can do. Now, what if there's 7 here and there's 3 to the power x? And we can't write 7 in terms of 3. Then how do we find x? This is where now mathematicians came together and say, okay, can we introduce a certain function? which will have a property that allows us to drop the power. So I said, okay, then I'm going to call a function that is an inverse of this exponential function. So what will be that inverse function? It will be called log. So how will they operate? So since we have y is equal to this guy, we'll apply log on the left of this guy, do the same on the right of this guy, and then let it be free that the power can come down. So we can write this as log of y is equal to x log of a. Said, okay. This means that if we're looking for x, then we can divide by log a, we can divide by log a. So these will cancel. And so x is going to be log y over log a. So we've done all this, we're just trying to find the value x. This means that if I have log of a as a base, and then I put y here is equal to x. Since this guy is an inverse function of exponentials, it should mean that if we lift this a is a base here where it is, it's called a base. And this x is an exponent. So we can write we can now move from logs to exponentials by getting the base. First we'll get this y and say y is equal to, we get the base a to the power x. This is how it was initially. Initially we had that guy. So what does this mean? This means that when we are dropping here, the variable x, we can as well choose not to operate with we can choose not to operate with just a log. We can choose to operate with a non-base, where we say, okay, so when it is y is equal to a to the power x, we don't want to have a fraction here. So what we'll do is we'll say log to the base a of y is equal to log to the base a of this ax. And then let it drop the power. So we'll have log a y is equal to x log a and keep the a there. So we're recording, don't worry. Then this means that log a y is equal to x. So, and then say, why should we keep this? Then we say, okay, this won't be kept. What will be happening is every time we have same things here, this will be vanishing to be 1. So that then we are able to find the value of x. So x is equal to log a y. So this is the direct inverse of y is equal to a x. So if you are given exponents, if you are given in exponential form, you can move to logarithmic form. If you're given in logarithms, you can move to exponential. This is a very critical relationship. This is what joins exponentials and logarithms. This is the link between the two. That's how you move from exponential to logarithms, from logs to exponentials.
Sir,
Hello.
I make a contribution according to my observation on the first one, and I didn't get it clear on when I said like log targeting log base log base a log base, yeah, just the log base a it's equals to 1. I didn't get it clearly. Then on the first one, I have my new method. I don't know if it can work. According to my observation, I've observed that what if instead of twisting those things, what if you just get a raised to power y? No,
A
down there,
raised
yeah, just there.
here.
No, there where
Yes.
you have to put the arrow
Uh-huh.
on top there. You
So,
get a raised to power y is equals to x. Then you just exchange the x and y.
So A raised to power y is equal to
X
x. And then when you want the
just there.
inverse, you
Yes, you
say
just exchange the
x.
y and x.
So we say A x is equal to.
Yeah, yeah.
Okay, anyway,
How
the whole
can it
idea,
affect you?
okay, we just want to be able to, okay, either way that you pick this, for as long as you understand that you're able to move from here to this part. In any way you understand it, it will be okay.
Yeah. Then
Because
on
you
how you came
understand
up
that
with,
this is, you're trying to say I can have an inverse relationship here, is it?
yeah.
But it should take you to logs. So I want it to take you to logs, whichever way it can take you there. Let it take you. So let's do this.
So now you came up with 1, sir.
With 1, what do you mean 1?
Yeah, there where you're saying log a is equals to 1. I didn't get the point. Yeah, just there.
Okay. Since we are saying that, log a of y is equal to x, implies that a to the power x is equal to y. This means if we have log a and a here, it means it is a to the power, this thing we don't know here, it should give us this a inside. It means that this thing we don't know is supposed to be equal to the power of a, which is 1. So the only number which can sit here, so that this is true, so that this relationship here is true, is 1. So say log a is equal to 1. And because you know that this one which comes here is what we get when you say a to the power 1. So we get a. So we'll put a. That's why we say so. Now look at this. Properties of logarithms. The first one. From this one, since we are able to write as that is a to the power 0, it means we have log a is equal to 0 here. So a power 0 is equal to 1. So it means inside here we need 1. Because of this one, log a y is equal to x means that y is equal to a to the power x. So it makes sense to say that log a1 is equal to 0. And so the log of a and a here, it should then be 1 because a to the power 1 is equal to a. We also see that now the critical one is if I have log a, let me put even x. And we want to change the base from a to b. Then we'll write as the log of base b, the new base. We'll keep x up there over the log of the new base b, and then a now will also be inside there. This one here is change of base. Change of base formula. Five, if we have the log of base a and then x being multiplied by y, please know that this is just the same thing as saying the log of a x plus the log of a y, for as long as the base is the same. The opposite of this one is if I have log a and then x over y, then we must get the log of a x minus the log of a y. And number seven, what has been left out? A bit critical as well. If I have log a power b of x, where a has the power b, you can bring down that b and make it the coefficient and remain with a without any power there, x. This one, don't forget, we'll do examples here. So it means that then we should also have, if we have a x to the power n, it should make sense that n can come down, and then we'll have log a x. This is the one that we used when getting the relationship there, that you can actually drop the power x if you apply log. Then the ninth one is that what else? Okay, I think these are enough. This should be enough. So there'll be no negative things here. Okay, maybe to mention that the log, if the base is 10 of x, you can also write as log x just without the base. And the 10th one is that if the log is e, you can just write as ln of x without the base. So if you find ln, then you know that the base is e. If you find just log, then you know the base is 10. So keep this. We are coming to do examples. When we get back, so we'll cool down for 5 minutes and join at so 5 minutes. This is 57. So join at 19:03 because it will be cutting at 57. 19:03. So those who watch on YouTube, please remember to always practice when I give a task as well. You can practice and comment on via mail. I read your comments. So just comment. Okay, so let's join at that time.